So yes, I want to tell you about a problem I've spent quite a lot of time thinking about, and probably some of these people on the front row will have a better solution by the end of the lecture. We'll see how far we go. So here's the scenario. We're at the IMO reception. Professor J is talking to the students here. Now there's somewhere out there 7 plates of delicious post-lecture snacks have been prepared, which is great news. The bad news is that, like all good academics, Professor J has beef. Professor J has a nemesis, Dr. X, who follows him around when he gives talks of this kind and has unfortunately decided to poison one of the plates of food. Now, we're not allowed to do this for real, unfortunately. It's health and safety. But we'll imagine this has happened. We'll imagine it's not terrible poison. We'll imagine that whoever eats that snack will fall asleep for 24 hours. So it's bad poison, it's not terrible poison. So what we'd like to do is we'd like to avoid that. We'd like to find the poisoned food as efficiently as we can. Now, what we're lucky to have sort of scattered around this room is a collection of IMO helpers. Now, what I can do, I know PhD students and undergrads are generally desperate people. I know that if I pay them £10, they will eat whatever I tell them to do. This is probably a reasonable assumption. Okay, now there is a problem here, which is, maybe Jane Street could handle this for me, but the state of academia isn't really great when it comes to money these days. So I'd rather not spend too much money on this. Okay, so the obvious idea is what I could do is I could get 7 helpers, I could give them a plate each, pay them £10 each, they each eat a plate of food. Now, even the people not on the front row should be able to work out 7 people, £10 each, it's going to cost us £70. That's pushing the budget a little bit these days. So let's see if we can do better. Now, my claim is here is a better strategy that is only going to cost me £30. So here is a strategy that I claim is only going to cost me £30. So what we have is we have across the top here, we have these different types of delicious food, and along here we have the 3 helpers, and there's a sort of plan for who's going to eat what. So for example, helper 1 is going to eat olives, breadsticks, dip and jelly. Okay? Now, what we will see as a result of this is, for example, something like this. I know I'm talking to young people, so I have to communicate with emojis. So what we have is we have helper 1 and helper 3 are asleep, helper 2 is awake. Now, hopefully, you can see what's gone on here. What you can see is that, okay, so if one of these plates of food was poisoned, we can see that this pattern of asleep, awake, asleep, matches the breadsticks. It matches the tick, cross, tick on the breadsticks. So what we can see is that from this pattern, we can see it must be the breadsticks that are poisoned. That's the exact pattern of ticks and crosses that matches the awake and asleep pattern over there. Okay, everybody happy with that? Now, if you think a little bit about what's going on, you can notice what I've done here. What I've done here is I've basically written binary representation. I've counted in binary. 1, 2, 3, 4, 5, 6, 7 in binary. So what that means is that whichever of these foods were poisoned, there's going to be a different pattern of ticks and crosses, and there's going to be a different pattern of awake and asleep over here. So my claim is that with this pattern of ticks and crosses, whatever was poisoned, we can detect it. Okay? That's my claim. Which is fine. So like I say, it would always work, but we're assuming that Dr. X is nice. We're assuming that there's only one thing that's poisoned here. Clearly, if there were 2 things poisoned or more than 2 things poisoned, this isn't going to work. And so what I want to put in your mind is I want to put in your mind a kind of bigger scale problem. So imagine instead of having 7 plates of food, maybe we've got 500 plates of food. Maybe we've got 500 plates of food out there and 10 of them are poisoned. Now all of a sudden, this starts to feel a bit more complicated, right? I mean, we start thinking about, well, what do you do with binary representations? How are you going to write this out? How are you going to do it? and it's not obvious. So the kinds of questions we might like to ask are, how many helpers would we need? How many people in general are we going to need to do this strategy? It's not obvious. What should we get them to eat? I mean, here on this previous pattern, we had this nice binary ticks and crosses thing, but is there a sort of comparable pattern of food that we could do it? Then, well, once we'd done that, once we'd designed some fancy pattern of ticks and crosses and people had eaten the food, how do we even work out what the poisoned food was? How do we go back and solve and find the poisoned food? Okay, so that's fine, but then what if this testing isn't actually very good? So what if, for example, some of the helpers are immune to the poison? What if some of the helpers have been pulling all-nighters writing Olympiad questions to go to the next room and are going to fall asleep anyway? So maybe the testing isn't perfect. What do we do then? So you can start to see that this is, it's already getting a little bit complicated. And this is group testing. This is what I'm going to talk about today. I'm not going to talk about everything we can talk about group testing, but I'm going to say something about it. But first, I just wanted to say a little bit of biography, just to kind of date myself here. So, as Dominic said, 91, 92, I did the Olympiad. I didn't do the Olympiad very well, but I did the Olympiad. 95, I did a maths degree in Cambridge, not at the college you're necessarily all thinking of, but at Cambridge. And 99, I did a PhD. So I think then, the kind of biography goes through like this, goes all the way through to 2024, I became head of school at University of Bristol. And so you might, if you started trying to fill in the gaps in here in terms of thinking, well, what does that look like? Then you're probably thinking, oh, well, Cambridge PhD, it's all automatic and, it all goes through like this. And really that's not the case. So the picture I want to show you is the famous Wald's aeroplane picture. I think when we talk about academic careers, I don't know if everybody knows this story, but the story dates back to the war and aeroplanes coming back having not been shot down. And so what people looked at it was they said, oh, look, this plane's been shot all over these places. What we need to do is we need to reinforce these parts of the plane. And actually, Wald, who looked at this, realized this is the wrong way to look at it. What Wald realized was these were the planes that came back. The planes that didn't come back were the ones that had been shot in the engine and in the cockpit. And so that's what you should be repairing. And so when you look at academic careers, you shouldn't look at the people who are standing on stage having become head of department. You should look at all the trajectories of all the people who went all through in different routes, that you're not seeing the people, I've had lots of papers rejected, I've had lots of grants rejected, I've been turned down for all kinds of jobs, and that's completely natural, that's how it goes. So I wanted to put it in a language that mathematicians in the room will recognise. IMO success is neither a necessary nor a sufficient condition for a successful academic career. So if you're sitting on the front row and you've got a medal, congratulations, brilliant, well done, but it's not all over. If you didn't make the team, or you're wondering whether you'll make the team in the future, plenty of my colleagues didn't go down that route. Some of my colleagues did go down that route, some of them didn't. And so it's something I wanted to say. In particular, in my research career, I very rarely look at functions where the year has been built into the function and I somehow have to find what the function is. I've never had to do that throughout my career as a mathematician. Part of the reason I didn't get a fancy medal was I couldn't do geometry. So I hit my wall at a particular stage with geometry. Combinatorics not great either, but But actually, I think there are interesting problems that you don't learn about in the Olympiad. So for example, I found my joy in probability. So probability is not something that tends to be in the Olympiad. And some of what I'm going to talk about is probability. And so probability led me into information theory, which is somewhere in my job title. And so I write theoretical papers, but also because I'm doing probability, I'm doing things that has applications. I get to work with people like engineers, computer scientists, biologists on interesting problems. So it's not the case that there's only this one route that you go and do a PhD and then it has to be pure maths and then there's lots of different routes. And actually, during COVID, a few people in this room will know I had lots of fun doing maths with COVID. Very, very basic maths with COVID, but got me on the radio, got me in the newspapers, and to me that was valuable. It wasn't complicated maths, but it was the right maths ideas at the right time. Okay, let's go back to group testing. So, well, what is group testing? So if you go home today and people say you went to a lecture, what was the lecture about? The lecture was about group testing. Well, what is group testing? Well, it's a way of efficiently testing a large population for a rare disease. That's the original motivation for the problem. That's how it was originally posed. It's also, if you're of a pure maths mindset, it's a combinatorics problem. It's a toy model that has some really interesting combinatorics problem that comes out of it. But then also, if you go back into my kind of applied way of thinking about it, it's something that crops up in all kinds of applied problems. There are problems in computer science, data science, cryptography, biology. There's whole places where this model keeps cropping up. So if you can understand the kind of fundamentals of the group testing problem, then actually you can find applications of it all over the place. So, brief plug, we have a survey about this. So this is a survey that went on the archive. For people who know the code, this means that this is a paper that went on the archive in 2019. If I had to give you career advice, then if you write a survey that can be used to solve problems in a pandemic, then putting it on the archive in 2019 turns out to be quite good in terms of getting citations. So if you happen to know there's a pandemic coming down the line, get your survey on the archive. That's the kind of career advice I'd like to give you. Okay, so let's have a little bit of history. So I said that this was a way of testing a population for a rare disease, and this is where this came from. So this problem was posed 1942, 1943, after Pearl Harbor. Literally millions of men were being signed up into the American Army. So millions of men were being conscripted into the American Army. And the American Army were worried that some of them would have syphilis. They didn't want to have soldiers going out and fighting that were infected with syphilis. And so what they wanted to do was to test them. Now, the problem is that the tests, they had tests, but the tests weren't cheap. So you're testing millions of people, you're testing one of them each. It's like paying the helpers £10 each. It's an extremely inefficient way to do it. Now, the situation, there was something that was helpful, which is that the condition was rare. Some people had syphilis, but maybe it was 0.5%, maybe it was 0.1%. So nearly all of these tests, we know what the answer is going to be. And so the point is that you never ask a question when you know what the answer is going to be already. You want to ask questions where you're going to gain information when you learn the outcome. And so just doing a single test where 99.9% of the time it comes back negative is a waste of time. And so what this guy, Robert Dorfman, suggested was he suggested that what you could do is you could take the blood, turns out it's a blood test, you take the blood and you mix the blood. So what you could imagine is that we could test this whole front row for syphilis at the same time. What we could do is we could take some blood from all of them. We could put it, it's a bit messy and unpleasant to think about this, but we could put it in a pot and kind of stir it together and mix it and test the mixed sample together. Now, what we will imagine is we will imagine a kind of idealized version of this, which is that if anybody in this sample does have syphilis antigens, then we will spot that. So if anybody has this condition, then the test will come back positive. So what we will know is somebody on this front row has the condition. Maybe more than one, but at least one has the condition. We don't know who. Okay? The good news is we might get to clear people with just one test. If this test comes back negative, we know that none of these people on the front row are infected. So what we've managed to do is by doing a single test, we've managed to clear the whole of the front row in one go. So potentially, there's some big savings here, right? So potentially, if we can get this to work, if our idealized test is accurate enough, then actually this will work. This potentially will tell us. Positive tests, we don't really know what to do with yet, but negative tests, we clear off a whole bunch of people really efficiently. And this is what we call standard noiseless group testing. Okay? So let's have a little bit of notation. I don't want to flood you with notation, but I want to get to a theorem. So what we'll do is we'll talk about the population. We'll talk about them as items. We have this slightly weird terminology. I think some of this came from kind of industrial process control. We'll talk about the population as being items. So items is the number of people in the population. And we'll say maybe that there are n of them. So there are n people in the population. We could imagine everybody in this room we're going to test. So that's our n. And then we'll do an idealized thing where we know how many people have the condition. We can say that's not realistic, but we'll pretend for now that we know how many people in this room have the condition. We'll call that number k. And the terminology, and it's unfortunate terminology, people talk about defective. This is the word that gets used. So we talk about a defective item is not a very nice way of saying somebody who has the disease. So what we'll imagine is that there are k people that have the disease, and we'll imagine that k is a lot less than n. We'll imagine that there aren't too many people in this room that have the condition, and we'd like to find them as efficiently as we can. Now, in terms of notation, sometimes we don't think about finding the people. What we could imagine is we could think about the set. We could think about curly k to be the collection of infected people. So what we'd like to do is we'd like to find curly k. Curly k is the collection of people who are infected. And what we will do is we will use this notation. We will have curly k with a hat on. Now, a hat is a fancy statistical way of saying I'm going to make a guess. We call it an estimate because it sounds more scientific, but k hat is going to be our guess. K hat is going to be, we're given the data, we're given the output of all of these tests, we're going to make a guess about the defective set. So what we'd like to do is we'd like it to be the case that k hat is equal to k. We'd like it to be really true that our guess of the defective set matches the true defective set. We don't know if we can do that or not, but what we could do is we could say, well, okay, we'll call that a success. So we'll say a success is that. So the probability of success is the probability that our guess matches the true set. Okay? Now, what we'd like to do is we'd like to get that success probability high, and we'd like to do it as efficiently as possible. So we'd like to use not too many tests in order to have a high success probability. Okay. Is everybody with me still? Everybody wish I would stop talking about mixing blood samples together and discussing stuff like that. There won't be too much more of that. Okay. Now, going back to my days in the Olympiad, one of the most powerful things I ever learned in the Olympiad was the pigeonhole principle. Okay? Score 1 for the pigeonhole principle. If you have more pigeons than you have holes, and you put the pigeons into holes, you end up with more than one pigeon in some hole. Okay? Now, that is an argument that gives us the most basic result in group testing. So the most basic result in group testing is as follows. If we want the success probability to be 1, then we must need at least what we're going to call T star. T star is what we call the magic number. T star is log to the base 2 of n choose k tests. So if we want to succeed, if we want to be guaranteed to succeed, then we need at least log to the base 2 of n choose k. So in that problem I was talking about, the problem I was talking about where I said we had 500 people, 500 snacks, 10 of them were poisoned, anybody that's really good in their head can work out 500 choose 10, take to the log to the base 2 of it, and they'll know they'll get about 67. So what we know is that we can't do this with fewer than 67 tests. If we had fewer than 67 tests, we're not going to be able to succeed. Okay? And the argument I just told you, the argument is literally the pigeonhole principle. Suppose we have t tests. If we do t tests, then there are 2 to the t combinations of test results. If you think about the awake, asleep column of people, there are 2 to the t of those. There are, each person could either be awake or asleep all the way down. So in total, there are 2 to the t. Now, if we want to be guaranteed to succeed, what we're trying to do is we're trying to find the defective set. And it must be the case that each of these possible defective sets, each of these possible n choose k defective sets, give us a different answer. So here's our pigeons, here's our pigeonhole. If we want this to work, it has to be the case that 2 to the t is bigger than n choose k, or if you want to take logs, you can say that t is bigger than log to the base 2 of n choose k. So there's a theorem, okay? So I'm not going to prove a lot of theorems and talk about lots of things I talked about, but something that we did prove, and I'm quite proud of proving, is actually that this magic number, things go really bad below the magic number. That what we proved this in 2013 in ISIT, what we proved is that for any algorithm, the smartest person in the room cannot come up with a better algorithm than this. For any algorithm that anybody comes up with, any test strategy, it is the case that the success probability decays exponentially below the magic number, that we have 2 to the minus t star minus t. So for example, if the magic number is 67, if you're only going to do 57 tests, then the success probability is going to be smaller than 2 to the minus 10. So the success probability is going to be 1 in 1,000. So there's almost no chance you will succeed if you go below the magic number. Doesn't tell us anything about what happens above the magic number, but it tells us that things get really bad really fast below the magic number. So there's no point in trying to beat the magic number. Okay, who does Wordle? Okay, keep your hand up if you do Wordle. Who got today's Wordle correctly? Yes, okay, people in this room got Wordle today correctly, and I'm relieved about that because that proves my theorem, okay? So there are, yeah, you put your hands down now, don't worry. There are, if you think about how you play Wordle, what you do is you take advantage of the information that you got as you go along. You have your favourite word that you guess at the beginning. Share is mine. Christmas Day, they gave us share was the word. Did you notice that? That there was apparently the most popular single word, and so they gave it to us. 2% of the population got Wordle correct on Christmas Day. Really nice present. But you know, once you put share in, once you see where those letters are, your next guess is you choose based on those letters that you've got already. That's called an adaptive strategy. So it's an adaptive strategy. Given the information that you got from the first test, you know what the second test is going to be. The first and second test tell you what the third test is going to be, and so on and so on and so on. Now, from the fact that some people put their hands up, we know that that works for Wordle. It doesn't always work, but if you play Wordle a lot, most of the time it will work. You can do it in 6. If you had to do it non-adaptively, you would have no chance. If you were to play Wordle, had to write down, at the beginning of the day, you had to write a list of 6 five-letter words, there is essentially no chance that you would succeed. So with Wordle, we know that there's this gap, that with Wordle, we know that adaptively we can do well, non-adaptively we have no chance. So the question is really here, does this matter? Because the simplest strategies that you can think about are adaptive. The simplest group testing strategies are adaptive. For example, what we call Dorfman testing. This was Dorfman's suggestion. So Dorfman's suggestion was, we have a large group of people, we split them into what he called pools, and we'll test the pools together. So for example, we test the first row together, we test the second row together, we test the third row together, and so on, okay? Now what Dorfman suggested was, well, we can do 2 things. What we can do is we can say, well, if the test comes back negative, that whole row's got a clean bill of health. We can cross all those people off. What Dorfman then said is that, well, if that comes back positive, let's just go back along the row. Let's just do individual testing along the row. So we'll look at the rows that came back positive. We know somebody on that row has the condition, so we'll test the people along that row. And actually people did this. People did this in Wuhan. I mean, not when COVID first arrived, but in June 2020, they tested the whole of the city of Wuhan. They tested 10 million people in a week. And they did it exactly using this strategy. They didn't have 10 million tests, but what they did was they split people into groups of 8. The groups of 8 that came back negative could go on their way. The groups of 8 that were positive, they tested them some more. And so you can believe that if COVID is rare, then this is very good. If COVID is rare, then this is a strategy that worked really well. But actually we can do a little bit better. I'm not going to go into details, but if it turns out that if the front row is too big, then actually going through and individually testing isn't brilliant. So if the front row had, say, 50 people along the front row, you don't want to do 50 tests. What you would do is you'd split the row in two. You'd say, okay, everybody to the left, 25 people there, we'll test those people now. If any of those are positive, we split that in half and so on. So actually binary search strategies are better. And it turns out there is something called Huang's algorithm. Huang's algorithm was in JASA, the Journal of the American Statistical Association, in 1972, which essentially achieves the magic number. So within a kind of constant amount, within kind of k of the magic number, Huang's algorithm is guaranteed to find all of the defectives adaptively using binary search. Okay, so we said the best that we could do was the magic number. Huang tells us we can get the magic number. Okay. Now, we could stop the lecture there, but the obvious question is, what happens non-adaptively? Now, there's two reasons we might want to know this. The first is, we're mathematicians, we're curious, we want to know what's going on in the world. We like to understand things. But then also, when it came to COVID, there was a practical problem here, that if we're going to do binary search, it's potentially going to take a lot of rounds of tests. If you had, say, 64 people in your group, if you have to split the group in half, 32, 16, all the way down, it would take potentially 6 rounds of tests to find all of the people. Now, early on in the pandemic, when they were doing this, these weren't those, you remember the lateral flow test that you could do and you get the result back in 5 minutes. It wasn't that, it was PCR tests. It was a PCR test. A PCR machine takes 8 hours or something to bake and come back with the result. So potentially, if you have to do this 6 times, each time it takes 8 hours, somebody's got to be in the lab doing this, takes a little bit of time to line it up. Potentially, with COVID, by the time you got the result, it might come back 5 days later and say, oh yeah, by the way, 5 days ago, this guy had COVID. And it's like, well, that's not useful information. 5 days ago, this person had COVID. He's given it to all of his friends now. So it might be that from a practical point of view, we actually want to do something faster. So there's a trade-off between the number of tests that we save and the value of each one. If you do tests, but it takes a long time to get the information back from the tests, it's not actionable information. Now, PCR machines are beautiful. PCR machines, you can actually do things in parallel. A PCR machine, what you can do, depending on which model of PCR machine you've got, which tray you've got, a PCR machine can test, say, 96 samples in one go. A sort of standard PCR test, it has little glass wells. It can test 96 different things. So what you can do is you can put mixtures of things in these different 96 wells and test them all in one go. So you test them all in one go. You get, in 6 hours, you don't just get one result back, you get 96 results back, which is great. But the drawback is that you need to declare the strategy in advance. You need to design what you're going to do in advance. You need to decide what the strategy is going to be before you do the very first test. And this is harder, right? This is, we said that this is more like the Wordle problem. So this is the fundamental question. How well can we do non-adaptively? Now, clearly, we can't do as well as we could do adaptively. We can't do better than we could do adaptively. Whatever the speed limit is for adaptive, that's going to be the speed limit for non-adaptive. But can we get close? The Wordle example suggests that we can't. The Wordle example says, no, it'll be way, way harder. We won't be able to get anywhere near the magic number. But actually, I'm going to show you some algorithms that will hopefully convince you that actually you can get close to the magic number. Okay, so this is what I want to talk about now. I want to talk about some non-adaptive algorithms. So algorithms where we decide everything in advance. So let's have some pictures. So here is a group testing scenario. So what we have is across the top, we have a bunch of people. So here are the people that we're going to want to test. What we will imagine is that, for the sake of argument, person 3 and person 5 are infected. So what we've done is we've very handily coloured them in red, okay? Now what I've done is I've just chucked some zeros and ones into this matrix. Before we had ticks and crosses where we were doing the food. I'm going to do ones and zeros. They're basically going to be the same. So a 1 means that this person is in this test. This person is in the test, this person is in the test, and so on, okay? So if we look at the rules of the tests, what we know is that this first test will come out positive, because what do we have? In this first test, we have person 1, 2, 3 who is infected. There's an infected person in the test, so the test is positive. This is going to be a positive test, okay? Test 3 will come back negative. Test 3 only has person 1 and person 2 in, okay? So this only has these 2 people in who are not infected, so the test comes back negative, okay? Everybody happy with the mechanics of this? Right. Okay, so what we could imagine is that this is how we could set up the problem. What we could do is we could draw a matrix of 1s and 0s. We could design a matrix of 1s and 0s, which is the test strategy. We will test the people, and they will come out positive or negative. Okay? Now, this is the scenario as nature sees it. But of course, we need to remember the pandemic would have been much easier if people who had COVID glowed bright red. If people who had COVID glowed bright red, we wouldn't have needed to do quite so many tests. Things would have been much easier. So actually what we have is this is the situation that we have. We have kind of the reverse of the problem. That was the setting that nature saw. This was the setting where we know who is infected. We can therefore deduce the positives and negatives. We are in a scenario where we don't know that. We have the positives and negatives, and we have a bunch of question marks along the top. So we have a bunch of question marks along the top that we'd like to make some sort of inference about who is and isn't infected. And we'd like to do this efficiently. So we'd like to do as few tests as possible. And if you think about it a little bit, maybe there's 2 different processes here. So there's one process, which is how do we chuck the 0s and 1s in? How do we design the matrix? And then how do we solve the problem once we've done that? What's our algorithm? What's our way of deciding the 0s and 1s once we've done that? Okay, so I want to tell you about the absolute simplest algorithm that you can possibly think of. So the absolute simplest algorithm that you can think of is called comp. And comp does the following. What comp does is it says the following. It says, okay, everybody that is in a negative test we know is non-defective. If they had the disease, the test would have come back positive. It didn't, so they can't be. Anybody that is a negative test, we give them a clean bill of health. We'll send them from the room. We'll say, you are not infected. You can go on your way. Okay? Comp then gives up. Comp then says, I don't know what to do after that. Everybody else is defective. Okay? I mean, it sounds a bad algorithm. It's not a terrible algorithm. It turns out that it's sort of somewhere on the page. But we'll see what the problem is. So what we can see is that here is a sort of toy scenario where we will do comp. So if we do comp, all we can do is we'll look at the negative tests. So the first test is negative. This one was negative. So everybody that was in that test we can send on their way. Person 1, person 3, person 6. They don't have the disease. They can go. Okay, do you have any other negative tests? Yes, we've got a negative test here. Test 3 is negative, so person 1 and person 5 also have a clean bill of health. We knew about 1 already, but we've gained that 5 is not infected. So we know in total 1, 3, 5, and 6 are definitely non-defective. We can send them on their way. We're absolutely confident in that. 2, 4, and 7, we don't know. 2, 4, and 7, we don't know, so we'll just say they're defective. That's our guess. Okay? Now, from a public health point of view, this isn't terrible, right? I mean, from a public health point of view, if you want to isolate people and be sure about it, nobody I've sent out into this world and given them a clean bill of health has COVID. There are probably some people who are isolating unnecessarily, so they're going to be cross. But from a public health point of view, from a kind of disease control point of view, this isn't terrible. I've found people and I've given them a clean bill of health and I've sent them away. So actually you can argue about this and you can say, well, the first stage is correct. If I tell you you're non-defective, you really are. There aren't any false negatives if you want to use that language. But it's not the best algorithm. It's okay, but it's not optimal in any sense. So can we do better? And we came up with an algorithm that, this is the simplest algorithm. We came up with the second simplest algorithm. The second simplest algorithm is what we call DD. So DD stands for definite defectives. So definite defectives, well, the first stage is the same as it was before. The first stage is you just look at the negative test. Everybody in a negative test, you just send on their way. Okay? Everybody in a negative test, you know they're not infected. You can get rid of them. So now there's a set of possible defectives, and now we do something smarter, ever so slightly smarter, with the possible defectives. So the possible defectives before, we just said, oh yeah, you've got it. Now, the thing is, before we didn't look at it, we didn't even look at the positive tests. We didn't bother looking at the positive tests. But what we could do is we could look for the positive tests. What we could do is we could look for a positive test which has exactly one of these PD items in it. Okay? That's the idea. So if you think about that for a minute, what we know is the test is positive, so it's got at least one defective in it. It's got at least one defective, there's exactly one possible defective in it. That must be your guy. That must be the person. So what we can do is I mean, it seems too stupid a step to be valuable, but this is the step. We will look for positive tests that have exactly one possible defective in. That item must be defective. And then the other ones, again, we're going to guess. The other ones, again, we'll say, oh, yeah, I don't know, fine, go on your way. You're non-defective. So just to kind of show you an example of this, what we can do is, if you remember what we did before when we did this comp problem, what we did was we found that 1, 3, 5, and 6 weren't infected. We sent them on their way. They had a clean bill of health. But now, what you can see is that the matrix has got better. That before, this matrix was bad. Okay, there was this positive test here, and it had loads of people in it, but we don't know which of them are infected. But somehow, magically, by the fact that we got rid of the black people, the people that we knew had a clean bill of health, all of a sudden this test that started off with a bunch of positives actually only has one. So we've got rid of the non-defective people, we've got one question mark. So the question mark we know we can shade in red. Similarly here, this test has exactly one question mark in, so we can shade that in as red. Okay, so we can find the 2 of these defective people. Up to this point, the inference is correct. Up to this point, we haven't made a mistake. We don't know about item 7. Item 7, we don't know what to do with. Item 7, you can argue it either way. They appear in a positive test, but it's a positive test that's already explained the fact that it's positive because it's got a red person in it. So we don't know what to do. So we'll guess. We'll just say, oh, they're probably negative. It's probably okay. So like I say, this is probably the obvious algorithm. I think if I sort of set you a way to think about this problem, I think very soon lots of people in this room would come up with comp. Not so long after that, some people in this room would come up with DD. But the thing that's surprising is that actually what we can do is we can prove performance bounds for DD. That what we can do is we can prove theorems and say, this is how many tests we need for DD to work. What it turns out is that this, what seems like a kind of rare event, this event that you have exactly one defective that hasn't been explained, turns out to happen a lot. It turns out to happen enough that we can take advantage of it. Now, I'm not going to prove a whole bunch of fancy theorems. I'm not going to, have long involved proofs you'll be pleased to hear. I'm going to show you a couple of pictures, but I want to at least answer the question, which is, how do you design the matrix? This matrix, this test matrix, how do we decide who gets tested? Now, there are 2 schools of thought to this. So one of which is that you do something very, very clever and fancy and structured and beautiful and inspired by clever ideas in pure maths. There are people in this room, that's how they think. I am a bear of little brain. My answer is I will chuck people in tests at random. And that's good. That's fine. So here is my argument. So the argument is that, well, how do we choose the test strategy? Well, in general, comp and DD should work. If with a decent design, with enough tests, comp and DD should work. And so our hope is that a sensible, and I don't know what that means, but a sensible random matrix will perform well on average. So if we take our matrix, if we pick 0s and 1s at random in a sort of sensible, structured way where we've done some calculations that tell us what sensible means, then actually that turns out okay. This is a very common argument in combinatorics that this is one of my frustrations about the Olympiad. The Olympiad, because you're not allowed to do probability, because back when Leonid Brezhnev was in charge of the Soviet Union, they didn't have probability, so it's not allowed in Olympiad questions. There are beautiful things that you can do with probability in combinatorics. What you can do is you can say, on average, there exists this thing, therefore we know something exists. It's a beautiful argument. It's brilliant. We should do it all the time. It's a very common strategy in combinatorics. It's called the probabilistic method, and I'm going to advertise for it here. And the most basic thing that you could possibly do is, what we could do is we could do what we call Bernoulli P. So what we do is we just pick a probability, we pick a number P, and every item ends up in every test independently with probability P. So what we do is literally every single person, every single test, we just flip a coin with success probability P, and we put them in the test with that probability. The clever part is how you pick P. P turns out to be 1 over k, well, 1 over k plus 1 over k. So there's a clever choice of P. If you make the clever choice of P and do things in this way, then actually this algorithm works great. So a very, very simple design will work well. So that's the most basic design, the Bernoulli design. It's easy to analyze, you can prove theorems. It turns out you can do slightly better. There's something that we developed later called constant column weight, where what you do is everybody gets tested a fixed number of times. You decide how many times everybody gets tested. Everybody gets, say, 10 tests. And then those, which of those 10 tests you get are chosen at random. That turns out to be slightly better. It's not obvious that it's better. But those are the kind of level of argument that we were using. We were using a Bernoulli design where everything's done independently, or constant column weight where everything's nearly independent. And what it turns out is that we can actually get very close to the magic number. So this is what this picture represents here, that this is the problem I posed at the beginning. We have 500 people, we have 10 of them are defective. Here is our magic number. Here is this graph that decays away exponentially, this 2 to the minus t thing decaying away exponentially at 67. What you can see is we're actually more or less on the same page. So if we simulate it, this is comp with Bernoulli, this is DD with Bernoulli. You can see that already with about 100 tests, maybe just over 100, DD is succeeding half the time. It's not like Wordle where you're completely off the page. With the constant column weight, comp is a little bit worse. Constant column weight DD is pretty good. With 100 tests, we said the magic number was 67. You couldn't do better than 67. With 100 tests, if you simulate it, this thing is already doing pretty well. There's another algorithm here called SSS, which I won't talk about, and that is in some sense the optimal algorithm. So what you can see is that there are these different algorithms. You can design the test strategy, you can simulate this, and you can see that actually we get close to the magic number. The magic number that there's this sort of obscure theoretical framework, this obscure theoretical barrier that we don't know if we're going to be able to get near. Actually, for this size of problem, you know what, we can do pretty well. We can get pretty close to it. Which is nice. That's simulation. Here's a theorem. I'm not going to really tell you what the theorem means. What we do is we kind of let n go to infinity. This is the sort of scenario here. We can prove things. What we do is we say, for various kind of complicated reasons, that k is n to the theta, that there's some fixed theta such that the number of defectives is a power of n. So for example, k is the square root of n, or the cube root of n, or the fourth root of n, or whatever, and we let n go to infinity. And we study something that we call the rate. And this is an information theory idea. The rate is basically what proportion of the magic number of tests do you need. So if you could do it in the magic number, you'd be up with this green line. What it turns out is that, for example, DD and constant column weight, we can get up to here. We can get that this is, I think this is natural log of 2. It's something like that. It's about 0.7. So what this means is that we need 1.4 times the magic number. This DD, this stupid algorithm, we can prove will succeed. This isn't a simulation. This is a theorem that says that this is how well we will be able to do. And so what we can see is that we're very much on the same page. We're not right up close to the magic number, but we're on the same page as the magic number. We're twice as much as the magic number, and we can prove that. Okay, I'm nearly going to stop. People have probably been thinking, well, this isn't very realistic. this is a toy model, and you'll be absolutely right. So there are a lot more realistic versions of group testing. This is the basic group testing. What if we don't get binary outcomes? What if we get some we just can't tell? You know, the lateral flow test just came back messy. We can't decide whether it's defective or not. Maybe we don't just get a 0 or 1. Maybe we get more outcomes. Maybe, like I say, there's noise here. Maybe the test isn't perfect. Maybe the noise depends on the number of people in the test. Maybe the more of these samples that you mix in, the blood gets diluted, the worse the test is. Yeah, we can study that. I said, let's imagine we know the number of defectives. That's obviously a toy assumption, but it just makes the explanation easier. But maybe the number of defectives, maybe we don't know it. Maybe there's some kind of community infection structure here. Maybe that, for example, if you're thinking about COVID, then if I'm infected, other people in the same house are likely to be infected as well. So I'm kind of assuming everything is independent. But more realistically, people who live together are more likely to be infected together. So can we take advantage of that kind of community infection structure? And so these are the kinds of things that people are studying now for group testing. The basic model is more or less solved. I think there are results that tell us more or less everything. A lot of these problems are still open. So if people want to work on these things, people want to find some interesting problems, download our survey, have a go, get stuck in. Thank you for listening.
Thank you very much for this talk, showing how it's a relatively short journey from some simple Olympiad-style problems with binary numbers right through to the state-of-the-art of this sort of culmination of decades of work with algorithms that can actually be useful and were used and are used. I think we maybe have, unless I'm told otherwise, I think we have time for 1 or 2 questions. Please, let me give you a microphone.
Hi, thank you for the talk. I was wondering, when you talk about reverse engineering who's infected from test results,
Yep.
that feels very similar in spirit to SAT solving, like looking at modular and kind of brute forcing but in an intelligent way. Are your algorithms better than those? Are there a specialized version of those?
It's a very good question, yes, and this is again a bit above my pay grade, but SSS, the thing that I didn't tell you, Sorry, I was clicking on the slide and it's gone. So the SSS algorithm is in some sense like a SAT solver. The SSS basically says find the smallest collection of infected people that are consistent with the exam with the results of the test. That is a really good algorithm, but it probably takes exponential time. It probably takes exponential computing resources. We can prove how well it does, but for almost any size of problem, it's not going to work in real time. And so there are better bounds that you can do that come from, there's something called a set cover problem, which is, I believe, is an NP complete problem. And so, yeah, you get into deep water quite fast, but yes, it's a good question.
Okay, so in that case, I think I'll say that if people want to hear more from Ollie, he has a blog, which, you'll correct me if I get this wrong, it's called Logging the World, and especially parents thinking in advance about Christmas shopping might be interested in his book called Number Crunch, which is recently available in paperback, if you want to see more along these lines. But I think all that remains is to thank Ollie again for a wonderful talk.